Ok, alors c'est un plaisir et un honneur pour moi de vous présenter aujourd'hui José Torero, professeur et directeur au Department of Civil, Environmental and Geomatic Engineering de University College London. José ici est un expert mondialement reconnu et récompensé à de nombreuses reprises pour ses travaux sur les sciences du feu. Et dans le cadre du dispositif Bridge de l'UFR d'ingénierie, José est professeur invité pendant 3 semaines à D'Alembert. Et vous pouvez le trouver notamment chez Suzy, qui l'accueille aimablement en 55 65 522. Bien, alors, présenter le parcours qui a amené José jusqu'ici, c'est un challenge risqué. Alors, risqué parce que José n'est pas tout à fait casanier. Donc, José, tu fais oui de la tête, et puis tu me corrigeras discrètement si j'ai fait des erreurs après ton séminaire. Hein. Alors, José a grandi au Pérou et ses études l'ont amené à UC Berkeley, où il soutient sa thèse au Department of Mechanical Engineering en 1992 sur une étude de combustion courante en micropesanteur. Et d'ailleurs, cette expérience a volé à bord de la navette spatiale américaine. José débarque ensuite en tant que postdoctorant à Poitiers, où le CNES va lui offrir le soutien pour développer une expérience visant à affiner la compréhension des structures de flammes non prémélangées établies en couche limite en micropesanteur. Les travaux de José prospèrent déjà à l'époque au sein du groupement de recherche micropesanteur fondamental et appliqué, GDR piloté à l'époque par René Gatignol et Roger Prudhomme, qui sont bien connus ici. José est alors recruté comme chargé de recherche en 1993. Bien, donc j'accélère un peu la frise chronologique, vous allez comprendre pourquoi. En 1998, José quitte la France pour un poste de professeur associé à l'Université du Maryland. En 2002, il traverse à nouveau l'Atlantique et devient professeur à l'Université d'Édimbourg. En 2010, il passe une année supposément sabbatique à l'EPFL en Suisse. En 2011, bon, voilà, il change carrément d'hémisphère. Il part pour Brisbane, à Queensland University. En 2017, il revient à l'Université du Maryland, mais l'Europe l'appelle à nouveau et il devient en 2011 professeur à UCL, donc à Londres. Voilà. Alors, je me permets quand même une petite note personnelle à cette introduction. On ne fait pas tout ça sans un modèle humain consistant. Je fais partie des nombreux étudiants à qui José et sa femme Michel ont transmis la passion de la recherche en les accueillant à de nombreuses reprises au sein de leur foyer. Et inversement, José et Michel ont fait partie des premières personnes à faire la connaissance de ma fille puis de mon fils. Alors j'essaie de propager ce modèle à mes propres étudiants tels que Kachif, Agnès, Augustin ou Yutao qui ont soutenu donc à D'Alembert. Bien, alors pour revenir à la science, José nous parle aujourd'hui de Understanding Extinction of Charring Materials. Et parmi ces charring materials, on trouve en particulier les éléments structurels en bois ou timber. La cible de l'exposé me paraît effectivement tout à fait adaptée à l'auditoire du jour. Thématiquement, D'Alembert revendique effectivement des recherches sur le développement durable des structures, sur l'interaction des structures et des écoulements, sur les leviers que proposent justement ces écoulements pour maîtriser la propagation de flammes. Et géographiquement et culturellement, évidemment, D'Alembert se sent éminemment concerné par ce qu'il est advenu de la charpente de Notre-Dame, pas loin d'ici. Voilà. Donc, José, nous t'écoutons avec attention.
Merci beaucoup. Alors, je vais me permettre de parler en anglais si ça ne vous gêne pas. Et c'est un petit peu plus simple. Et je pense que ça me permet de parler avec la présentation de façon un peu plus fluide. So I'm going to be talking mostly about timber, but in general, it's a concept associated to charring materials. And charring materials are materials that when exposed to high temperatures, they're going to go through a process of degradation, pyrolysis, and instead of fully gasifying or melting, they produce a layer of carbon as a residue. And the layer of carbon has a major impact on the way in which the material behaves. Now, the reality is that layer of carbon, from the perspective of fire safety, has a very positive effect. because a layer of carbon represents a heat transfer barrier that then, as it grows, is going to prevent heat from further pyrolyzing the material, and as a result can lead potentially to extinction. And it is that extinction that makes these materials viable. Now, in terms of retarding the capacity of a material from burning, we have done for many years around the world enormous amount of progress trying to convert plastics into charring materials in an effective way, keeping their mechanical properties, keeping their optical properties, and still guaranteeing that that transition is not a transition that goes through melting and gasification, but it's more a transition that goes through charring and then potentially gasification. So this process is a mechanism that we use to try to use materials in a way that is fire safe. Now, obviously with the aspects of sustainability, now timber as a natural material is becoming a very relevant proposition as a structural material. And industry has developed a multiplicity of products, cross-laminated timber, laminated veneer lumber, you can name it glue-lams, all these products that basically deliver structural elements with exceptionally homogeneous and high-quality mechanical properties. So that now we can design timber buildings in a way such that they are very reliable, and we can create shapes and forms while maintaining the overall homogeneity of the properties of the material. So in the past, we had to cut a tree, and then we will get a big log, and that log had imperfections, had problems, and those became the weak links. So when using them as structural elements, you had to make them massively redundant to be able to guarantee that the mechanical properties were appropriate along these different complex structural systems that many times have a very large scale. Now, with these new products, there is a combination of adhesives and timber. You can construct whatever structural element you want and guarantee that the structural element has fairly homogeneous properties. There are no weak links, and therefore you can optimize the design appropriately. So that has pushed enormously the use of timber into construction, and we've seen an enormous change in the way in which we're introducing timber now into the construction industry. Now, just to give you a little bit of a sense of the evolution of tall buildings in the last 2 or 3 decades. If you look in yellow, this is the evolution of tall buildings with structures that are non-combustible. In the y-axis, you have basically a percentage of increment in height, and you can see this massive transition with the Burj Khalifa in Dubai, where effectively from the previous building that there was a Sears Tower or the Willis Tower to the Burj Khalifa, there's an increase of almost double. Okay. Now, the reality is that now the same thing 10 years later is beginning to happen with timber. But not only is double, but in a period of 10 years, we have tripled the height of the tallest timber building. And the rate at which this is increasing is extraordinarily steep. And in many of the big cities in the world, now we're seeing exceptionally tall timber buildings that 10 years ago were completely unexpected. Now, if we look at that image, it only gives you half of the picture, because the other half of the picture comes at actually taking every single one of these buildings and actually looking at the reality of the number of buildings that are coming in and changing this. So if you look at non-combustible buildings, actually the Burj Khalifa is an anomaly. It actually increased very rapidly, but all of a sudden, very rapidly, we went back. And we've been very slowly increasing the height, and we can see the tendency. So each of these data points corresponds to one of these buildings that you have there. Now, in contrast, when it comes to timber, the change has been completely different. Now, why? Because we have been pushing changes in legislation that now allow timber buildings to be constructed at any height. And most of this data here are actually timber buildings in the United States and Canada, where the legislation has eliminated all caps on height, so you can build timber buildings at any height. They're a little bit more conservative in France, a little bit even more conservative in the United Kingdom, but that's changing, and we're seeing a lot of buildings coming up in Europe right now, pushed mostly by the Swiss, the Austrians, the Swedes, who are developing a whole industry around the construction of timber buildings. Now, so the problem is significant, and the change is quite dramatic, and it's actually quite rapid, and it's also quite extensive. You know, this is not a small number of buildings, this is a very large number of buildings that are coming in. So now, the real question is, what is the problem of using timber as a structural element? Now, the reality is that if you look around you, you know perfectly well that we can design and exist safely in buildings that are filled with charring materials. Every chair in this room is a charring material. Every book in the shelves is a charring material. The vinyl on the floor is a charring material. So it is not that we don't know how to design buildings for the usage of combustible charring materials. But when it changes from being the contents of the building to the structure of the building, what is really the problem? And why is it so different to design a structure that is made out of timber as opposed to designing a building that is filled with timber or cellulosic or charring related contents? And the question is not a really easy question to answer, because it's not as straightforward. You know, it's a real complicated problem that requires us to go straight back into what is our definition of a safe structure when it comes, to its performance. So, when we look at timber, there's been extensive work on structural safety. People have studied robustness, durability, combustibility, but not as much its fire safety. We design buildings, but the question is, are we introducing fire safety appropriately? These are the real questions we need to ask ourselves. And basically, what is what we really expect, from the performance of a timber structure? So, we have a structure, and a structure has a function, and that function has to deliver something. And that something has to be the same, whether the structure is made out of timber or whether the structure is made out of a non-combustible material. And that functionality is what we need to be able to understand. Now, because the reality is that all buildings, independent of what material they're made of, have to deliver the same level of safety. We cannot accept to use a structural material that actually performs less than others. At the end, the level of safety is part of a social agreement, and this is what we expect from all our buildings. You're all sitting here, and I presume you all feel that you are safe, no? Because we have because we have accepted that the way in which this building was designed gave us the right level of safety, and as a result, we walk into these buildings confident that those buildings are actually safe, and therefore, no matter what structural material is being used, it has to deliver that. So whether a building is made out of a combustible or non-combustible materials, the building should achieve the same level, of safety. Now, interestingly enough, the definition of what a safe structure is when it comes to fire is a very old definition. It was jointly developed between the United States and the United Kingdom, and that definition has permeated around the world for a very long period of time. So in 1928, a gentleman called Ingberg created the concept of fire resistance. And that concept of fire resistance established that a structural system has to be able to withstand the burnout of all the combustibles in the building and still perform its function. So in other words, a structure can never fail. So in essence, if you burn everything in this room, all the structural components still need to be able to deliver their structural function. Now, why was this established in such an extreme way? Because they were thinking at the time, in the early 1910s, 1915, they were thinking about building skyscrapers, very high buildings, where it was very difficult to guarantee that people could evacuate appropriately. So the structure could not fail. And therefore, the way to guarantee that the structure will not fail is by guaranteeing that the building will withstand the burnout of all the fuel that was available within the room. So basically what they did is they sent people around looking and documenting how much fuel you had in an office, in a hospital, in a residential building, and they created a whole chart of fire loads, which were statistically distributed. And then you have a statistical distribution of the fire load that tells you how much combustibles you have. And that basically became the fire load that was applied to the structure. And as a result, you had to demonstrate that your structure could withstand the total consumption of that fire load. Now, during the Second World War, this was studied very deeply for completely the opposite reasons, because we had designed all these buildings to withstand burnout. And the question was now, how do you destroy them? So everybody worked very, very hard in trying to figure out how to overcome this design to create maximum levels of destruction, because there was an understanding that the way you affect morale is much more significant through extensive destruction produced by fire than through localized bombing that not necessarily was creating the same level of or extent or the damage. So this is what is called the post-war building studies, which was a compilation of all this effort that was done all over the world. I mean, every person that claims to be a father of the discipline of fire engineering stems from the post-war studies. So Kawagoe in Japan was trying to destroy American cities. Emmons in the United States was trying to destroy Japanese cities. Thomas in the United Kingdom was doing the same thing for German cities, and so forth. So all this was put in place, and the conclusion was the structure will retain its function until the burnout of all the available fuel. So that is the performance criteria. Okay, so that's what we are designing for today. So now, if we look at that concept then, here is a typical room. You're going to have combustible linings, which are part of the furnishings of the building. You're going to have furniture. These are all part of the furnishings of the building. You're going to have non-combustible linings, like, for example, plaster or concrete. And effectively, what you're doing is designing for burnout, which is a complete consumption of all the combustible linings and combustible furnishings. So everything here that is combustible has to burn out, whether it is a lining or a furnishing, and the room will look like this at the end of the fire. Nevertheless, the structure will remain intact. Now, if the structure is designed of non-combustible materials, and we take, for example, a typical office building, you will find that you have an average of 60 kilograms per meter squared, more or less. I mean, even if you take all these bookshelves and you actually spread them around the room, you will find that you will be within an error bar, but you will be around 60 kilograms per meter squared. Okay, so if I'm designing a non-combustible structure that's made out of steel or concrete, I will take the energy generated by this and apply it against, or do a heat transfer calculation to calculate the evolution of temperature of the structure, then look at the evolution of the material properties, do the appropriate structural mechanical modeling, and come up with a way by which I demonstrate that this non-combustible structure doesn't fail. In other words, continues to fulfill its function. Now, when I have a structure made out of timber, how can that be achieved? Because in essence, as this starts burning, potentially the structure will start burning too. And now you don't have 60, but you have about 5 times that. So you have about 300 kilograms per meter squared. If you take about 250 kilograms per meter squared, which would be the average weight of a structure. So how can you design thinking that you have to retain the function until burnout of all the combustible furnishings? The only way by which you can achieve it is by guaranteeing that once the combustible furnishings stop burning, the timber will just simply extinguish by itself. So if the timber extinguishes by itself, the structural timber extinguishes by itself, and you have to do nothing about it, then you would have fulfilled exactly the same performance criteria. Okay? So it is actually a problem of extinction. It's a problem of demonstrating and understanding how timber actually extinguishes by itself, and being able to create conditions within the building that guarantees that once the heat flux coming from the combustible furnishings stops heating the timber will slowly decay and extinguish itself. Okay? Now, and this is really, really important because the consequences are astronomical. And you can see that, for example, in what's been happening this week in Los Angeles, where you have this massive forest fires, pseudo forest fires, but they're actually now urban fires that are effectively igniting one building after the other one after the other one and propagating across the city, destroying the entire city. We are back to the 19th century with these urban conflagrations now in places like Los Angeles. Now, why? So this is a picture in Los Angeles, okay? If you count the stories, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stories, okay? So this is now a typical modern timber building. This is a 7-story timber building that caught fire in Los Angeles a few years ago. This is the tallest building in Los Angeles, which goes to 310 meters in height, and this is the height, more or less, of the flame. Now, can you imagine the level of radiative heat transfer that is coming out of that? Now, the way by which we prevented urban conflagrations is we assume that the fire was going to be a 1-story fire. We calculated the radiation, and then we imposed a decay function that allows us to guarantee that the adjacent buildings will never ignite. So we turn an urban conflagration problem into a building problem, because if you have a fire in a building, the fire will never propagate to another building. Now, by introducing timber buildings, if we don't guarantee self-extinction, the consequences are going to change dramatically, because now your characteristic length scale is the height of the building. And once your characteristic length scale becomes the height of the building, you can find yourself with 300-meter tall flames. And we know what happens then. I mean, we've seen it this week in Los Angeles. The moment the flame becomes too big, there is nothing we can do. It would just simply continue to spread. Okay? And unless the winds change and they push where there's no fuel and it's fortuitous, you can deploy as many firefighters as you want and throw as much water as you want with Canadairs, you will never stop it. The amount of energy that is being released and the fluid mechanics of these large plumes are so complex in nature that they're extraordinarily difficult to stop. Okay? So you can see the importance of not changing this small length scale into this massive length scale. So the consequences are potentially very severe, and therefore the reliance on self-extinction is really fundamental, and therefore we need to understand the process properly. So here's a very simple test by which you take a piece of timber. This is a CLT. This is a radiant heater, and you heat up the material. You allow it to ignite and burn. And you can see you have a burning rate of approximately 6 to 8 grams per meter square per second. And as soon as you take the heat flux out, you can see that the burning rate decreases and eventually disappears. You know, and this is the process of self-extinction. Okay? And normally this happens because at the interface where the timber converts itself into char, you don't have enough energy reaching so that you can produce sufficient amount of gases to maintain the flame temperature to a point that is above the quenching temperature. Okay? So the process is actually quite straightforward, and but its understanding is actually not that simple. So if you look at the problem in a little bit more detail, here's a section of the timber, and you basically take the surface is the char surface. This is the pyrolysis surface, and you have a heat flux that is going in from the char into the virgin timber. That is what is going to sustain the pyrolysis of the gases. then the pyrolysis gases have to penetrate a porous media, which is the char, and then emerge to the outside as a burning rate. Now, at the charring surface, you're going to have your external heat flux provided by any other heating source. You're going to have the heat from the flame that is established on the top, and you're going to have losses to the environment. Those could be radiative or convective, depending on the configuration, and the net heat flux is going to result in heat coming in to the char. The energy balance between what is going out and what is going in is the change of energy within the char. Now, what we can see is that if we apply a heat flux, eventually what we get is the heat flux that is going in is going to reach a steady state. Now, that's the worst case condition, because by the time you reach steady state, this gradient here is going to be the heat conduction to the inside is going to be minimal. So that will give you the worst case condition. So in essence, you want to study this problem at steady state. Because if you get it right at steady state, that's the worst case condition with the minimum gradients, and therefore then everything else will be better than that earlier in time. So we take the energy balance, and we take all this, the flame plus the external plus the energy produced by the char oxidation at the surface, is going to be equal to the pyrolysis, energy required for pyrolysis, the heat going into the virgin material, and this is the term that basically goes steady state. So the losses are the heat going out and going out in this way. Now, and we define this term omega, which is basically just a normalized amount of energy that you need to guarantee the pyrolysis. So if I rearrange this equation and I just normalize it by the heat losses, then what I get is effectively this term. This is the pyrolysis, energy required by pyrolysis, and this is the supply of the flame. So every kilogram that needs to be pyrolyzed is going to produce this amount of energy. Okay? So if the amount of energy produced is greater than the amount of energy required, then it continues to burn. So this is an equivalent to a mass transfer number. Okay? And it is all done once you have attained steady state conditions. Now, when you look at this expression, then you can go a little bit deeper and do a high activation energy analysis, very similar to what you will do with a counterflow burner, and basically change all this into a critical Damköhller number. So basically, what is the critical Damköhller number? In this case, there's going to be two. There's going to be the critical Damköhller number for the gas phase, for the flame, but it's also going to be a critical Damköhller number for the oxidation reactions at the surface. Now, this becomes a really important parameter because, in essence, when you think of the problem, is if you have a system where you provide heat, you're pyrolyzing, you maintain a flame, and at the same time you're oxidizing the char doesn't grow. So in essence, when you attain steady state, you have a certain char thickness that, because it's thin, it will still allow for pyrolysis gases to produce and still to have a flame going on. Okay? Now, if you quench the oxidation reaction, then the char continues to grow and then inevitably goes to extinction. So in essence, what you need to guarantee and what comes out of this analysis is purely that you have this critical Damköhller number for quenching that is fundamentally related purely to char oxidation. And when we run a whole series of experiments and we started looking if there was a critical condition under which you went from this condition where you had the steady state situation where char was oxidizing and therefore the thickness of the char remained thin, and the process continued to go to a point where there's a transition, and that transition is associated to the quenching of the reaction. Now, how do we identify the quenching of the oxidation reaction? By basically looking at a ratio of the experimentally calculated Damköhller number to the theoretically calculated critical Damköhller number. So you calculate the two of them. Technically speaking, the ratio should be 1, unless you made a mistake. Now, because in our analysis, we used oxidation and pyrolysis to calculate the critical Damköhler number for the flame. If the oxidation disappears, then our Damköhler number becomes artificially large. So the moment that you go from 1 to this artificially large value, you know that you have quenched the chemistry of the oxidation reaction. And that allowed us to establish a critical condition in terms of the incident heat flux that effectively allows you to establish the moment where char oxidation stops. And the moment where char oxidation stops, then you know that you have the condition that would lead to self-extinction. Okay? So now, why is this very useful? Because the external heat flux is something that I can construct by just simply looking at the fire dynamics of the compartment. As everything burns out and there's no more energy being produced in the compartment, all I have is heat exchange through convection and radiation from the walls. And that radiative convective environment within the compartment is one that I can calculate. And if that compartment is producing more than 30 kilowatts per meter square, then the system will continue to burn. If it's producing less, eventually will lead always to self-extinction. So there is a fundamental set of principles that governs self-extinction of timber elements, and the question is trying to create those things and looking at them in a way that is actually practical. So this is a series of tests that were conducted at a very large, sort of larger scale. And basically, we were looking at what were the cases where the flame extinguished, what were the cases where you still had burning rate. In other words, there was still combustion going on, and there's obviously a range of transition. And you can actually find that that sort of same limit that we had looked of quenching in the analysis is a limit that more or less remains when you start doing macroscopic type of experiments. And once you go below 30 kilowatts of an external heat flux, char oxidation will stop, and then all of a sudden the problem goes slowly into self-extinction. So at the end, what is the criteria? So the criteria is that an external heat flux promotes char oxidation, attaining a steady state char thickness that allows to always have a Damköhler greater than the critical Damköhler. As soon as the external heat flux decreases, then basically char oxidation reactions stop, and then you get a Damköhler number that is less than the critical Damköhler number, and you get self-extinction. So the heat transfer environment within the compartment is the one that defines that external heat flux. So then you can convert these critical Damköhler numbers into a critical heat flux for self-extinction, and basically you evaluate the problem against that critical heat flux for self-extinction. Now, the reality is then, how do we apply this? Because at the end, we need to demonstrate this. No? So we need to make sure that if we model the fire and model the thermomechanical behavior of the structure until burnout, then basically that leads to self-extinction, and that basically allows me to satisfy that. Now, you will say, well, straightforward, no? So now that I have the criteria, now that I know what is the functional requirement that I have to meet, then, well, I go and model the fire dynamics. So if I have the compartment furnishings burning, they basically produce a net heat flux that is going to be applied to the structural elements. I just put a simple one-dimensional version of the heat transfer equation. And I input the temperature evolution in space and time to a structural analysis. And then the structural engineer can do his analysis and determine that the function still retains. So the thermomechanical analysis done by the structural engineer will work. And that has to be done for an imposition of this fire load that imposes the net heat flux from time equals 0 to the time to burnout. In other words, until you consume all the fuel within the compartment. Is that okay? So in essence, the problem, technically speaking, is not complicated. And then when it goes to the structure, this photograph in the background is a photograph that dates from the late 19th century, and it's a photograph of a factory actually in France, where you have the steel beams hanging on top of a timber beam. And there's a timber beam that has self-extinguished, But nevertheless, the heat was enough to completely destroy mechanically the steel. So in this particular case, the timber actually performs better than the steel. And now, what do we have here? If we look at a thermomechanical behavior of just a simple beam, what we have is that if we heat the beam, there's going to be bulk heating that is going to result in thermal expansion, but there's also going to be temperature gradients because of the imposed heat flux, and those temperature gradients are going to expand the lower vein more than the upper vein, so you're going to get curvature. And as a result, the combination between the bulk heating and the reduction due to curvature, the difference between the two of them is what is going to give you effectively the stresses and strains within the mechanical system. Okay? Now, you can normalize that. Here's the bulk expansion minus the shrinkage, and you can do a simple geometric analysis to find out what is going to be the shrinkage, and then you can demonstrate by modeling when it's going to be buckle, when it's going to buckle, what kind of deformations you're going to get. So technically speaking, if you have the thermal fields in the solid, you will know what the mechanical properties are, and you will know more or less how to model the structure. So in essence, if you think about it, I can actually do the fire, then get the temperatures for the structure, then do the structure, get the mechanical behavior for the structure, and technically speaking, demonstrate the functionality of the system. Now, unfortunately, the problem is much more complicated than that, because these are complicated products. Okay? And when you start looking at these complicated products, you're going to have different forms of mechanical failure. You're going to have, obviously, burning. You're going to have charring, potentially extinction. But you're going to have product-induced thermomechanical behavior. So, for example, when you start heating this, the material that is being heated, as it loses moisture, is going to contract. And the moment it contracts, the glue lines or the adhesive lines become failure modes. And basically, you have material that splits. This is called delamination. And the splitting of the material results in pieces of timber falling down and feeding the fire. So it basically increases, your fuel load, and therefore creates a bigger problem. The mechanical behavior can change dramatically because it's a composite system, and under certain forms of heating, the failure can be on the timber. Under other forms of heating, the failure can be on the glue lines. And it can be on the glue lines horizontally, or it can be on the glue lines vertically. So there's all sorts of different forms of behavior that we need to be able to understand, and those problems are actually, unfortunately, not easy, to resolve. Nevertheless, we are designing tall timber buildings. So how are we doing it? And these tall timber buildings are being put up, and I can absolutely guarantee you that any of the engineers who were involved in the design of those buildings, first of all, doesn't understand the concept of self-extinction or a Damköhller number. Needless to say, they will not understand any of the concepts that you have there. So how are we doing it? Because we are putting 40-story timber buildings in cities. I mean, there's one going up here in Paris as we speak. And it's really interesting and merits the question. So let me explain how we do it. Okay, so how we do it today. So how we do it today is we say, well, we have hazards, and we're going to design the building under ambient temperature loads. Okay? So all civil engineers will understand a dead load, a life load, wind load, seismic loads. They put them all in there and they design the building. With that building, they create a conceptual design. Okay? And that conceptual design is basically the main system, the main structural elements, the envelope, the bigger parts of the building, and it's a structural system. Now, structural engineers learned to recognize years ago that there's actually such a thing as fluid mechanics. And fluid mechanics interacts with solid mechanics in a very interesting way. And you create loads as a function of your decisions of what a structural system is. Now, the perfect example is wind loads. So why do we do wind tunnel studies with structural elements? Because we know that if we change the shape of the building, we change the shape of the fluid mechanics, and we change the pressure distributions in the building. And as a result, because we change the pressure distributions on the building, we completely transform the loads that reach the foundations. Okay? So this is an example, again, of the Burj Khalifa. So this was a study that was done in Canada by Skidmore, Owens and Merrill. And effectively, they did CFD modeling of the tower, and they also did this wind tunnel study, in which basically they played with the section of the building to try to minimize pressure loads. So they recognize those interactions, and because they recognize those interactions, they know that loads can be optimized. So you can actually play with the shapes in such a way that you get the minimum amount of loads created in the problem. So there is a process of optimization that allows me to convert the wind velocity into pressure in an optimal way. So the concept is recognized. Nevertheless, when it comes to fire, it's actually not applied, despite the fact that in the case of fires, temperature is actually quite an obvious one, because if you think about it, if I change the surface to volume ratio of any structural element, I change heat transfer. Okay, so in principle, the same thing that I've done with wind, I should be able to do with fire, but we decide to ignore it, and we go straight into section sizing. So civil engineers will go and define what the size of the beams, the columns, and everything is going to be, all the details, and they get final detailed design, all done assuming ambient temperature. Okay? Now, as I said, the thermal mass and the surface area are going to dominate the heating rate. So if I change the shape of my structural elements, I will completely change the way in which they heat up. So in essence, I should have recognized that and introduced that into the optimization, but I'm going to decide to ignore it. And as a result, I'm going to go to my detailed design, completely ignoring that. Now, we lose a very important degree of freedom in the optimization process, because in essence, I could be choosing my sections in a way such that they give me the best behavior for fire. But I don't. I just simply ignore it. Now, a lot of people do nowadays what we call topology optimization, by which they try to put the mass in the right place so that they get the perfect or optimal structural behavior. Now, that leads to extraordinarily little thin elements that have a very, 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 very small mass and a massive surface area, which are going to fail immediately in the event of a fire. So for people like me, topology optimization is topology de-optimization, because we're going in the opposite direction, where we're creating elements that are going to be fusible elements that are going to be failing immediately. So, but anyway, that's the way we do it. Now, so how do we currently capture the fire load? Very simple. As I say, the amount of fuel has been statistically determined. People have been doing surveys, mostly insurance companies, and they've come up with an amount of fuel that is the fuel load, FLED. Okay? So if you divide the fuel load by the burning rate, you get the time to burnout, which is what we want. Now, the time to burnout is therefore a function of the fuel load. But this function is highly nonlinear. Okay? But what we do is we just say, well, let's forget about the fact that it's nonlinear. Let's make it a linear function, without recognizing that if you look at all the different properties of a material, just if I take geometry as a characteristic value, the burning rate increases dramatically as I play with this thing that is called the ventilation factor. The top part is the flow rate of air into a system. The bottom part is the total surface area that loses heat. So this is heat generation, heat losses. And as a function of this ratio, the burning rate is going to change dramatically. So if you have a very high ventilation rate, a lot of energy gets produced, you get very high burning rates. If you have a very low ventilation rate, little energy gets produced, you have low burning rates. All this is ignored. And we basically assume it's a constant value somewhere in the middle, which is 0.8, and then we just go with that. Okay? So we've passed that impasse. Now we have a burning rate. But how do we get that burning rate? Then we actually do a furnace test. Now, what is a furnace test? We're going to put our structural element inside a furnace where we control the temperature of the furnace, which is a really interesting question, no? Because we all know that temperature is not the same as heat flux. Nevertheless, the way in which we run the test is we run it as a function of temperature. What we are controlling is the temperature, and we're calculating the burning rate by fixing the temperature to a standard temperature time curve. This standard is ISO 834. Every country has its own number, and effectively it is just basically what we call a standard temperature against which we will subject all structural elements. Now, if we look at different thermal conductivities for different materials, you will find that if what I am controlling is the temperature, the heat flux is going to change with the thermal conductivity of the material. Furthermore, if the material ignites, the heat flux is going to be negative. So the entire premise by which we determine those burning rates, and people have placed, well, maybe this curve is not enough, let's do a different one. But they're all temperature-based. And at no point we are determining heat fluxes. All that we're doing is basically creating some sort of surrogate number for the burning rate as a function of a test that was defined in 1928, where effectively temperature and heat fluxes were not necessarily considered to be that different. So in essence, we have created a test that is just a surrogate. And that surrogate has no bearing with reality because it is based on temperatures and it is not based on the control of the heat flux, which is the parameter that you should be interested in. So once we've done that, then how do we address our design? Well, what we say is, well, there's two ways in which the timber is going to change. One is going to lose section. Two is going to increase in temperature. Okay? And that increase in temperature is going to make the timber weaker. We can see the mechanical properties drop almost to zero by the time you get to 300. So it's going to make the timber weaker. So I have to increase the cross section. So I add a corrective, sacrificial increase to the cross section. Okay? Now it's going to lose section because of charring. So I create a charring rate based on the furnace test, and basically add a sacrificial layer, another correction. So what I'm going to be doing is just designing everything in cold, and then adding the charring correction and adding the thermal correction. And those two corrections are considered to be enough to be able to establish that the system is going to work. So in essence, I'm just simply going to enhance the section, E epsilon T, and then I'm going to enhance the section epsilon char to correct for charring rates and to correct for temperature increase in depth. Okay? So as a function of that, where do I get the charring rates? I get them from the furnace, despite the fact that we know it's not appropriate. And where do we get the temperature in depth to calculate this? We get it from the furnace. Okay? So as a result, we get a fire section correction. And that's how we design timber buildings today. Okay? So once you get the correction, now you have a correction sizing, then now you have to go and ignore the fact that this is a composite, where part of it is timber, but those timber elements are glued with adhesive. And the temperature of the adhesive and the way its mechanical properties drop, by 90 degrees, the adhesive has no mechanical properties. So they're very different to the loss of mechanical properties for the timber. Nevertheless, I ignore that. So I don't pay any attention to it. Now, another problem is moisture migration, because water is going to migrate through the porous media, and we know that then it's going to accumulate and you're going to have very high moisture levels. Now, the problem is that the decrease in mechanical properties with moisture is extraordinarily fast. So as soon as you start increasing the moisture content, your mechanical properties go down to zero. And as a result, you get concentrations of stresses and you get the material cracking. So the material splits because there's no mechanical strength here and there's more mechanical strength here, and therefore at the shear layer, then the two of them you're going to find your cracks. So none of the things are incorporated. They're all somehow ignored. Now, once we ignore all that, Then we go and design the connections. But we also decide to ignore that the connections are going to behave weird because they're going to be expanding and rotating, and those need to be designed in an appropriate way. And we know that the heating and the cooling processes are going to be very different, and the connection is going to lose strength. All I'm going to do is just put a safety factor. Okay? And now I have a safety factor that I'm going to use to optimize. So basically, I design the connection in cold. Everything is done in cold. I design the connection and put the right connection so I get the smallest sections and do an optimization process. And that brings me to my performance assessment, which allows me to make decisions whether I reject the design or whether I accept the design. That's how we design buildings today. So the fire resistance test remains the surrogate for the fire, and we ignore everything, you know, and therefore just basically follow that surrogate as being the approach. Now, if you go through the pages of the Eurocodes, the Eurocode for timber design was issued about 8 months ago. It has been a process of revision for about 6 years. And they've basically redone this all over again. There's almost no changes on the previous one. All that there is more correction factors, more safety factors. So now, you know, you used to have section multiplied by chi 1, chi 2, chi 3, chi 4. Now it's chi 1, chi 2, 3, 4, 5, 6, 7, 8, 9, 10. But in essence, none of these features are incorporated into the process at all. So now, can you circumvent all this complexity? Yes, you can, if you guarantee that self-extinction happens, you know, very fast. You can see the beautiful pattern of charring. When you get this perfectly homogeneous, extraordinarily well length-scaled patterns, is because you have a single characteristic length scale, which is a very thin char. If you have a very thin char, the cracking, everything becomes a very homogeneous pattern. You know, it protects heat transfer into the solid, so none of this other shrinkage and deformations and splitting and moisture happens. If you wait until this happens, everything comes your way. Okay? So in essence, going back to extinction, you know, what you need to do is basically guarantee self-extinction as soon as possible. Okay? Now, you're going to say, well, but you cannot control how much fuel you have in a compartment. No, you can't, but you can control the geometry. So if I make a compartment taller, or I change the ratio of the windows and things, doors and things of the sort, I can actually change the thermal environment. And I can make sure that that critical heat flux happens, decrease of critical heat flux happens very fast. And as a result, I get a very, very thin char layer that gets formed before self-extinction occurs. And then the process becomes one that enables you to circumvent everything. So how do you do that? Here's a series of tests that we conducted. And you can see that the fire starts, it grows, it reaches a peak. You have a very, very violent fire happening, and then all by itself, very rapidly, it dies out, and then you get self-extinction. Now, if you play with the different conditions, you find how the QNet starts evolving, and you can find conditions by which your time to burnout is 15 minutes, in which case you get a very thin char layer, and you circumvent all the complexities of the problem. Designing in cold becomes rational, okay? Now, if you allow the fire to continue burning and the heat flux to continue, the QNet to continue to increase, eventually you're going to get to conditions where the system starts delaminating, pieces start falling off, they start feeding the fire, and the fire never stops, and then you need the firefighters to kill the fire at the end. That's a condition you don't want to have. Okay? Now, can you play with all this? Yes, you can play with all this by actually playing with the geometry of the compartments. Now, which basically brings another challenge, which is that you need to inform architects so that they can actually understand when designing the volumes and the spaces, that they have to design them also so that the fire actually works correctly. So at the end, if you do that, then you can change the process and you can introduce the fuel as one of your loads. Then you can do your conceptual design and you can generate those loads. And now you can introduce not only things like wind, but you can also introduce fire as part of your initial optimization process that defines the general or conceptual structural design. So at this point, you're talking to the structural engineer and the architect, and they are designing things in a way that they already introduced this and guarantee me self-extinction where my char layer is this thick. Is that okay? So once you do that, then you can now size your sections, connection detailing, and then you can do your performance assessment. And the process becomes infinitely simpler because you've circumvented all the complexity. So you can make your decisions and have a building that works. So given what I just said, do you think that we're ready for this? It's a really, really, really big question, because the bottom line is that at the end, this is a matter of lack of competency. We have a construction industry that is moving at a very, very, very fast speed, driven by sustainability drivers that are pushing the construction industry in a direction that the actual participants in the design process are not competent enough, because they don't understand anything that I just explained. Now, the tools that we give them, the Eurocodes and so forth, do not incorporate these things either. So in essence, we're moving into a space in which the process of design that we are implementing is not a process of design that is directed towards resolving what really matters, which in this case is the self-extinction of the timber. Thank you very much, for the attention. Happy to answer any questions.
Thanks for the talk, Jose. I'm back to the rate of charring.
Yeah.
So I have a question about the. So you say the fastest. The faster the rate is, the best way it is to protect the material, or is that what you are saying or not?
I mean, basically, the best way to protect the material is to attain the critical Damköhller number as fast as possible.
As fast as possible.
As fast as possible. Yeah. Why? Because, but the as fast as possible is how the rest of the room is burning. So if I have a room with this furniture, okay, and this ceiling height, with those windows and those doors, this is going to produce a lot of heat for a very long period of time. So you will not attain self-extinction until much, much later. So you will have a lot happening with your structural element. So the char would have progressed quite deep. It would have probably started affecting the glue lines. It would have created contractions, all sorts of different things. Now, if I double the height, then the thermal environment in here would have dropped below the critical flux very, very rapidly, very early on. It's still going to be burning, okay? But it's going to drop below the critical heat flux, so the timber structure cannot continue to degrade, okay? So basically it dies, and then you have self-extinction already, and therefore the charring thickness doesn't grow, and then the problem becomes very superficial.
Okay. And so my further question is about the oxygen content that you have. Can it play a role in this?
Yeah, it does. I mean, normally when we design buildings, we assume that you will have plenty of air coming in. So you will always have enough to burn what is burning, okay? So because obviously windows can break, doors can be open. Now, but the reality is that if you had a very small room, and that very small room had the door closed, the smoke layer will descend to the ground very rapidly, consume all the oxygen, and the fire will die. But we cannot rely on that, because obviously the practicalities of oxygen supply are very different. Now, obviously, if you're looking into aircraft or spacecraft, then you can control that variable, but in buildings you can't.
Can you explain again how the geometry of the room affects the?
Yeah, so maybe I can. I don't know if this works, but if you have a room, and that room has an opening, the supply of oxygen here, through the mass of air that can get in, determines how much oxygen gets in here. Okay. Now the walls determine how much heat losses you're going to get through the walls. And so if you multiply this amount of air by the heat of combustion per kilogram of oxygen consumed, then you get the heat generation. Okay? And if you multiply the losses by the area of the room, then you get your heat losses. Okay? And in minus out gives you MCP dTd time. Okay?
Thank you for your presentation. I was just wondering concerning the char layer.
Yeah.
It gets thinner with oxidation.
Yes.
And I was wondering if it was possible to add inhibitors.
Yes, it is. I mean, I think it is quite interesting. So there's a range in which you can actually play with the chemistry of char oxidation. So you can actually introduce chemical products that will actually change a little bit, the limits of char oxidation. So the chemistry can be played with, but not very much. And that's the key, because the char, keep in mind that the char is the product of the degradation of the timber. So anything that you do to the timber will undergo first a pyrolysis chemistry, and then you get the char. So a lot of the effect that you have on the timber itself will be diluted by the time you get to the char. So you can only change it through a very, very narrow range.
Thanks for the presentation. Just one question. I know for steel beams, for example, it's quite common to protect them if they're in an environment that is subject to heat. Is that not an option for wood beams?
Yes. So one of the options is to encapsulate, the beam. So basically to put non-combustible cover. Now, from an aesthetic perspective is a problem because the timber disappears. Mm-hmm. And from a sustainability perspective, plasterboard has more embodied energy than concrete. So the more layers you put of protection, the less sustainable credentials the timber has. So yes, but it can be. I mean, a way of addressing the problem is by basically turning the timber into a non-combustible material by covering it, with plasterboard. Yes. Now that is very common with steel, where you actually use insulation. Mm-hmm. And but in the case of steel, the only purpose of the insulation is thermal. So basically, all you want is to reduce the heat transfer to the steel. In the case of the encapsulation with timber, you are not only reducing the heat transfer, but you're trying to prevent ignition. Okay, and so if the plasterboard was to fail and open a crack, then you basically, it's the mechanical failure of the encapsulation that then becomes very significant, because once the timber ignites, then the whole process, is a different one. So it's complicated on the reliability terms, and it is very, very complicated in trying to justify from a sustainability and architectural perspective. But for example, the Brock Commons in Canada, which for a while was a 32-story building, was the tallest timber building in the world. You don't see there's not 1 square centimeter of exposed timber. Everything is 4 layers of plasterboard encapsulating everything in the building. So it's done.
Okay.
Last question.
Yeah.
So currently we do tests with a fixed temperature profile.
Yeah.
How would you do this with a fixed heat flux temporal evolution experimentally?
Yeah, we develop a test called the H-trace, which basically is a radiant panel. So you have a radiant panel that provides a constant heat flux. Okay, and by moving back and forth the radiant panel, you can change different heat flux profiles. Okay, and so that's sort of the way we do it. Obviously, it's much more complicated now, because you have to evaluate the convective heat losses and use that as an input to a control system that moves the panel back and forth, so you can get the constant heat flux. But effectively, what you get is your sample, and you get a radiant panel that is moving, as the temperature increases, to guarantee you a fixed heat flux at the surface. Okay.
Thank you very much.
Thank you.